Hello! Today we're looking at a brand new topic called volumes of revolution. Specifically, we're looking at volumes of revolution about the x-axis. But what is it, you may be asking? Well, to understand that, let's take a step back to something we've done in Maths A level already. If you've got a graph with an equation of a line or a curve, represented in the format y equals a function of x, then you can find the area between the curve or line and the x-axis by integrating the equation of that curve between the limits a and b, where a and b give the horizontal boundaries of where that region will start and finish, thereby giving you the area you require. This is a really cool method because it allowed us to find the areas of not just boring normal shapes like rectangles and triangles, but also really crazy curvy areas as well. Because as long as we're comfortable enough to deal with the algebra involved, the method will find the area between the curve and the x-axis, which is pretty neat. But the thing is, this is 2D, a 2D area. And you know what's cooler than 2D? 3D. So, what volumes of revolution does is this. It still takes a line or a curve and considers the region between that line or curve and the x-axis, if we're doing volumes of revolution about the x-axis. But instead of leaving it as a 2D region, we're then now going to view it as a 2D region in a 3D space. What we're then going to do is we're then going to attach the bottom of that region to the x-axis, and then use the x-axis as an axis of rotation. So we're going to rotate this region 360 degrees about the x-axis. We're going to consider that any space that the region travels through as it's rotating will leave behind a 3D volume in its wake. And therefore that will lead to, in this case, something that looks like this. This is really cool because it means we can calculate some really crazy volumes of things. Because, okay, we had a rectangle in this case, but if we have a more crazy curve, it will end up calculating the volume of that shape as well once it's rotated about the x-axis. But how do we actually do that calculation? Well, if we have the equation of the curve or line that's bounding the 2D region, if we want to then find the volume of the solid formed when we rotate that region 360 degrees about the x-axis, worth pointing out the exam could say 2 pi radians about the x-axis alternatively, then this is given by the formula pi lots of the integral from a to b of y squared dx, where y is again, just like it was for normal integration, just being used as a placeholder for the equation it represents in terms of x. It's worth pointing out this is not a formula in the formula booklet, so you are going to need to remember it. But there is a very easy way you can use to help you remember what this formula is. Ultimately, it looks suspiciously like the formula for the area of a circle, pi r squared. And this isn't a coincidence. Normally, if we're using integration to find area, of course, if we're looking at a more simple example like this rectangle again, then of course the height of the rectangle was decided by the y value of the line we had, and then the width of the rectangle ended up being decided by the limits on the integral. So hence why we do the integral from b to a of f of x. But if we now extend this idea to what's going on with the cylinder, the volume of a cylinder is normally calculated using pi r squared for the area of the circle at the front times by h, the length of the cylinder. But of course, now instead of r for radius, we're going to have again y representing that length for whatever line or curve we're using for whatever volume we're looking at. And then, to deal with the width, instead of just having y as a static thing, we've got to integrate it over the interval b to a. So hence why we end up with pi lots of the integral of y squared with respect to x. b and a telling us where we're starting and where we're finishing. Okay, so that really is the majority of what you need to know in order to be able to do this. It is just a formula and then using your integration skills you already have from before. So let's take a look at an example. We've been given this region R, which is bounded by the curve that they've given the equation for. And it's the area between that curve and the x-axis, so just like we normally would have if we're just integrating x's. And we've even been given the limits x equals 0 and x equals 2, where the areas starting horizontally and finishing. Now, admittedly, sometimes it's worth pointing out they'll be mean and not give you those limits and just expect you to work them out based on visually what's going on the graph. For instance, for this question, you can see that the area is starting and stopping where the x-intercepts are happening. So therefore, you maybe could have been asked to find those limits just by having to work out what the x-intercepts are. But anyway, we're not leaving this as a 2D region, we're then going to find it as a volume by rotating it 360 degrees about the x-axis. So all you've got to do is use this stuff in the context of the volumes of revolution formula. So therefore the volume is going to equal pi lots of the integral from 0 to 2 as our limits of 2x squared minus x cubed, but this is volumes of revolution, so we've got to square that equation, and we're going to be integrating x's. So what we've got to do next is we then therefore got to square out those brackets. So, making sure we do it properly. Admittedly, I am skipping some working. Some of you may choose to use a grid method or something like that to ensure you do this accurately. Because whatever you do, you don't want to be dropping marks for silly mistakes on basic algebra. Cool. So then giving ourselves a bit more room on another page, we then just progress on by now proceeding to integrate. Don't forget that pi out the front, but then we're just going to have x to the power 4 integrating to x to the power 5, dividing by the new power to get a coefficient of 4/5, and then the x to the power 5 integrating to x to the power 6, minus 4 divided by 6 is minus 2/3, and then lastly we're going to have 1/7 x to the power of 7. And of course still the limits 2 and 0. And then although the next part is ultimately just a bunch of number crunching, we're still going to show ourselves manually plugging in the limits, because there's often a method mark for showing you understand how to use the limits of an integral. So I'm going to show myself writing out what happens if you plug in the first limit of 2 into everywhere that you see an x. And then, of course, subtracting from that, what happens if you also plug the limit of 0 in everywhere. Beyond that stage, you are welcome to then use your calculator more to help you out, do with the number crunching. But therefore, if you were to do that, you would end up with a final answer of 128 over 105 lots of pi. Don't forget the pi. Now, it's worth pointing out, an added note is that a lot of these questions often end up being wordy questions in exams, because it's very easy to apply this idea of volume to a real world scenario. We live in a 3D world, there's volumes all around us. So therefore, do watch out for those questions that you include units, if there's a context attached. And also in context questions, it's not entirely unusual, they sometimes want you to leave your answer instead of an exact form as a decimal. Obviously make sure you give it to the accuracy you asked, which is the default position of 3 significant figures, or pay attention to the wording in case they've asked for a very specific level of precision in the question. Another little detail I'd like to finish off with is you once again will have noticed that I squared before I did the integration. That is really important that you do that, because if you integrate then try and square out the stuff, it will get you an incorrect answer. Okay, hopefully you found today's video useful and interesting. I'll see you in a future video. Goodbye.